Okay, in this video we're going to run through the exam questions for quiz 6. There's some stuff in here on rates of reaction, and you've also got some CC5, which is ionic bonding, and CC6, covalent bonding revision, which you're going to need for your mock. So the first question, you're asked to calculate the average rate of a reaction. To get the rate of a reaction, you need the change divided by the time, and that change can either be a change in mass or a change in volume. In this particular question, you're told 15 centimeters cubed of gas was produced. Centimeters cubed is a volume and 15 is your change. So I've got 15 centimeters cubed is my change. And it tells me it takes 60 seconds. So my time is 60 seconds. Now, if you look at the answer, you're told to give your answer in centimeters cubed per second. I've got centimeters cubed, I've got seconds, so no unit conversions are needed. You get 1 mark for just doing 15 over 60. And then if you actually work it out and see that the answer is 0.25, you get your second mark. Second question is very similar. Again, you're asked to calculate the average rate. Again, it's going to be change over time. This time, again, your change is a volume, 90 centimeters cubed, so that's going to go on the top. But they give you the time in minutes, 5 minutes. And again, if I look at the unit in my answer, I can see that it's in seconds. So what I'm going to need to do first is I'm going to need to convert 5 minutes into seconds. We know that there are 60 seconds in each minute, so it's just going to be 5 times 60 is 300 seconds. And instead of dividing by 5 here, I'm going to divide by 300. Then I've got centimeters cubed and I've got seconds, the 2 units that I'm being asked for in my answer. When I do that, 90 divided by 300, I get 0.3. So you get 1 mark for writing this, 1 mark for actually converting your minutes into seconds, and then 1 mark for evaluating your answer. So 3 marks for doing that. The next question we're going to skip because we haven't done tangents yet, so I'm going to skip over that. I'm going to move over here to question 9 instead. So the student wants to investigate how the size of marble chips affects the rate of the reaction. They want different size marble chips. How can they get them? So marble chips are like little solid pieces of rock. You're not going to be able to cut them up with a scissors. Instead, you're going to have to crush them. So you can say you crush, and the thing that we would typically use to crush them is called a pestle and mortar. Okay, so don't say cut with scissors, crush with pestle and mortar, something to do with that. And you're getting 2 marks for describing how you can make those large pieces smaller. And the next one over here, you've got a graph, and you are asked to explain in terms of particles why the rate slows down as the reaction takes place. If we look at the graph, we can see it starts off steep, which tells me the reaction starts quickly. Then gradually it becomes less steep, which tells me it slows down. And when the graph fully flattens out, it's not just slow, it is completely stopped. And what they're asking you here for 3 marks is to explain in terms of particles why this slows down as the reaction takes place. Now, to answer this, you're just going to have to explain that the particles get used up as the reaction takes place. If you end up with less particles, you're going to get less frequent collisions, and eventually the reaction will stop. So we'll just say, alright, between, does it say which one's in excess? No, so we're just going to say, as the reaction takes place, magnesium and HCl get used up, and there are going to be less particles, and then there are going to be less frequent collisions. Less particles and then less frequent collisions. Okay. Next question is based on practical, so you would have done this. You want to keep a conical flask at 45 degrees Celsius throughout a reaction. What do you do? A Bunsen burner is not going to work. Okay, you can't control the temperature of a Bunsen burner in the same way. What you're going to use is a water bath. If you put it in a water bath that's set to 45 degrees Celsius, it will stay at 45 the whole way through. The next question again asks about tangent, so I'm going to skip over those 2 questions and then move over here to explain in terms of particles how decreasing the temperature affects the rate of this reaction. So we had something similar last week about increasing the rate, now they're asking us about decreasing. So if you decrease the temperature, if you're decreasing temperature, particles have less energy and move slower. If they're moving slower, they collide less frequently. And again, I'm always using that word frequently in these answers on particle collisions. All right, so that'll get you 2 marks. The third thing you need to mention when it comes to temperature is activation energy. If you decrease the temperature, less particles will have the necessary activation energy. So remember, activation energy is the minimum amount of energy that a particle must have to react. And if you give the particles less energy, less of them are going to meet that threshold, less of them are going to be able to react. All right, the next set of questions aren't on rates, they're all on a revision topic. The first one, describe what is meant by a covalent bond. You're not going to get any marks for saying the bond between a non-metal and a non-metal. You have to give me the definition, and the definition is simply a shared pair of electrons. You get 1 mark for saying shared electrons. If you remember to include pair, you'll get your 2nd mark. Why is chlorine a gas rather than a liquid? Okay, so if it's a gas, you know that the particles are far apart. If the particles are far apart, there must be a weak attraction between them. We've only learned about one weak attraction, and that is weak intermolecular forces. So you'll say weak intermolecular forces don't require much energy to overcome. Okay, so room temperature, which is typically around 20 degrees, there's enough heat at room temperature to keep these particles far apart because the forces between them are so weak. Okay, so if it's a gas, or even if you've been asked about a liquid, there's always going to be weak forces, and the only ones we learn about are intermolecular forces. This question is potentially a little bit tricky, okay? It says the ion of element X has 54 electrons. Now we can see that element X has a 2- charge, and that means that it has gained 2 electrons. So after gaining 2 electrons, it now has 54. How many electrons did it originally start with? Well, it started with 52. Okay, so it started with 52. It gained 2, now it's got 54. And if it originally had 52 electrons, then it must also have 52 protons. Okay, when it was an atom, the number of protons and electrons would have been the same. So you got 52 protons. And once you know the number of protons, to get neutrons, it's the mass number minus the proton number, which is going to be 125 minus 52 equals 73 neutrons. The next few questions are just about dot and cross diagrams. Okay, so they want you to draw one for water. They've drawn out the circles for you. Oxygen goes in the middle, hydrogen on either side. So hydrogen's outer shell is the first shell. The first shell can only hold 2 electrons. Hydrogen's got 1, and it wants 1 more. So if hydrogen gains 1 electron, it will have 2 in its outer shell. The outer shell is shell 1. Shell 1 can only hold 2 electrons, so it's full. Oxygen's outer shell is the second shell. It's got 6 electrons in there. The second shell can hold 8 electrons, so oxygen needs to gain 2 electrons. The number of electrons they want to gain is the number of electrons they are willing to share. So oxygen will share 2 electrons, and hydrogen will share 1. Okay, so when I come down here, I know hydrogen's only got 1 electron, and I know it's going to share that 1 electron. Hydrogen's sharing space with oxygen is in here, so I draw hydrogen's electron in that sharing space, and there's no electrons left to draw on the outside. The other hydrogen is going to do exactly the same thing. Then oxygen, we said, has 6 electrons that I need to draw. It's only going to share 2 of them. It's going to share 1 with this hydrogen and 1 with this hydrogen, and the other 4 electrons it's going to keep to itself. So once you've drawn that, you can do a few checks. All right, hydrogen's only got 1 electron. Make sure you've only drawn 1 dot for each hydrogen. Oxygen's got 6 in its outer shell, so make sure you have drawn 6 crosses. Make sure that oxygen has 8 electrons in its outer shell. 2, 4, 6, 8. Make sure hydrogen has 2, and it does. And also make sure that you've got an even number of electrons in the shared space, and I do. Okay, so that's my 2 marks. The next one, you're asked to draw it for oxygen. So if I'm drawing O2, I must have 2 oxygens bonded together. Again, we saw that oxygen has got 6 electrons in its outer shell. Oxygen wants to gain 2 electrons, therefore oxygen will share 2 electrons. So this represents oxygen. It's going to share 2 electrons. It puts 2 electrons inside the sharing space, but it's got 6 in total, which means there are 4 electrons that it's not going to share. The other oxygen does the same thing. It wants to gain 2, so it shares 2. The other 4 electrons it does not want to share, so it keeps them to itself. And if I add them up, oxygen now has 2, 4, 6, 8 electrons. This oxygen has 2, 4, 6, 8. So they both have a full outer shell. I've drawn 6 crosses. I've drawn 6 dots, which represents the 6 electrons in each outer shell, and I've got an even number of electrons in the shared space. The fact that I've got 4 electrons just means that I would have 2 bonds between those oxygen atoms. I would have a double bond because each pair of electrons represents 1 bond. I've got another one down here. I've got carbon dioxide. So carbon dioxide we know is CO2. The atom that's by itself is going to go in the center. So I'm going to put carbon in the center and I'm going to put an oxygen on each side. Again, I'm only looking at the outer shell. So carbon has got 4 electrons in its outer shell. Oxygen's got 6. So we've seen oxygen, so we'll start with oxygen. We know it's got 6 in its outer shell. It wants to gain 2, so it will share 2. So this oxygen will share 2 electrons with carbon, and it will keep 4 electrons to itself. This oxygen will share 2 electrons with carbon, and it will keep 4 electrons to itself. Okay, so I've drawn my 6 electrons for each oxygen atom. Now I've got carbon. Carbon's got 4 electrons in total. It wants to gain another 4 electrons because it wants 8 in total. So it's got 4. If it gains 4, it will have 8. And if it wants to gain 4, it means it will share 4. So it's only got 4 electrons and it's going to share all 4 of them. That means I'm not going to have any electrons in these bits. I'm only going to have electrons in the shared spaces. And if it wants to share 4 and you've got 2 sharing spaces, they'll be divided evenly between. So I'm going to represent carbon's electrons with open circles, and there's carbon's 4 electrons. Now if I do my checks, oxygen has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. I've got 6 crosses for this oxygen, 6 dots for this oxygen, and 4 of these open circles for carbon. So I've got the right number of electrons, and I've got an even number of electrons in each of the shared spaces. And that's the end of that.